Let's get started. So approach number one is due 1 week from today. We will discuss it a little bit during class, so it might be good to have it out when we get to it later. We will continue in Chapter 2, Part 1 notes as well. Were there any questions before we get going here? Okay, so we left off on page 42 last time. Just started talking about the non-parametric bootstrap. And so with the non-parametric bootstrap, what we do is we sample our y's from the f-hat distribution. F-hat is an EDF. And what this basically means is that we are going to resample with replacement from the original data. Alternatively, one can think of it this way as well, which we discussed, where let's say that we have y1 down to y12 as our observations. What we can do is focus on the indices here, so 1, 2, all the way up to 12, and actually basically sample the indices with replacement. So for example, maybe one resample might look like this, index 2, 3, all the way up to 12, and then we get 2 again. So that means that we have 2 y2s, 1 y3, down to 1 y12, and no y1s at all. And we can use this then, to tell us which of the y's we need in our resample. And that's exactly basically what the boot function R does when we use the non-parametric bootstrap. So let's talk about this air conditioning data example once again. What we're interested in is theta, which in other words is the population mean in terms of the number of hours that these air conditioners last. And we have a sample of size 12. And with this sample, we calculate our statistic T, which ends up just simply being the sample mean. So to do the non-parametric bootstrap in R using the boot function, well, first of all, we need to tell R that we're going to use the boot library, the boot package, I should say. And we need to write a function that actually calculates the statistic of interest. This function is very similar to what we did with the parametric bootstrap, but there's a small change to it. With parametric bootstrap, we had a first value within this function that we're going to pass in it. We had our data. Well, now, since we're using the non-parametric bootstrap, we also have to add a second argument, which typically you just denote as I, meaning I for index. So you can kind of think of how that might be useful then when we are calculating our statistic based upon resamples. And let me actually go on over here to 10 to do this. So typically the very first argument, so this is going to be calc.t. I usually will call this function calc.t, saying that we're calculating t. The first line in the function then is where I specify what my exact data is. So D gets data, and I want the I indices. So if I was 1, 2, 3, all the way up to 12, then that basically means I want my original data. And then I calculate my statistic of interest, the mean. So let's actually try this function out with my data, and simply the indices 1 through 12. And as you would expect, oops, sorry, let me get y back again. I was doing some other stuff earlier today that had something else for y. And there's my sample mean, 108, which we had calculated before. So the function seems to work. But again, to emphasize how this function is going to be used, what we could do, for example, is use calc.t with the original data, and then let's repeat index 1 12 times. So in other words, we might have, let's say, a resample that had simply y1 in it 12 times. And as you would expect, you get that particular observation back. or you get the observation y1 was 3, so we take the mean of 3, of course you get 3. But when we actually do this in terms of resampling, you could say that the I argument comes about through using the sample function, which we looked at the first or second day of class. And so we can say sample, and the first argument's x. It's just what's called 1 to n. So 1, 2, 3, all the way up to n, though, from those integers. Sample size of 12, because that's what my n is. And then replace equal true. So if I were to use this function once, just all by itself, you can see there is my resample, or in terms of the indices for the resample. If I do it again, I get different values because they use the same seed. In order to use the example in the notes, or to reproduce the example in the notes, there's set my seed there, and now I get 90.25 as the mean. So you can say that this is a t star. Is everyone clear on what calc.t does? Okay. There's an important point that I want to make here about constructing these kinds of functions. We're going to be doing these calc.t-like functions a lot throughout the semester. And right now our data is in a simple vector, y. Make sure that I didn't make that big enough. 16. But let's say instead that my data was in a data frame instead. So for example, let's let y2 be a data.frame that just simply contains y. And it just so happens the variable is called y as well. Now, what adjustment then do I need to make to my calc.t function so that it works? Because if I were just simply to implement calc.t with y2, look what happens. Error. What adjustment do I need to make to this function to get it to work? Now that I have a data.frame. Data frame, I should say.
When you're indexing data in I, do you need to have specified that it's a column?
Basically, it has rows and columns. So that would be the adjustment that I would need. Just to verify that indeed it works, let me run that new function. And there is my proof that it does work. Now the reason why I bring this up again is because often you'll be working with data that's maybe just in vectors or data that's in data frames. And from past experience in teaching this course, when I was working with vectors and had students in the first or second project work with the data frame and find out that they were unable to do some very basic calculations, that's why I bring this up now. Okay? Now, just to emphasize, this I says what row to pick versus what element to pick that we have with the vector. Okay, let me change back my calc.t to its original form. And now let's use the boot function. First I'm going to set a seed though to make sure I can reproduce my results. Put the results into boot.res. Could call it something else. I just decided to call it that because it stands for Bootstrap results. Use the boot function like we did with parametric bootstrap. Data equal y, my statistic equal calc.t. Let's say I want 1,000 resamples. And here is the main difference then with the parametric bootstrap. We say sim equal ordinary now. I don't know why they don't say non-parametric. They just say ordinary. And that's basically it. Now there might be other times where you need to pass in other bits of information into this calc.t. You'll see some examples in chapter 3. But for now, this is it. That's all we need. So let's do some bootstrap. And this is what we get. Okay. So to make sure that you understand what's actually being displayed here, when I just simply say boot.res, I've actually labeled everything here in the output. On tests before, I've actually asked students to label what this information is being displayed in terms of the correct formulas. Also on tests, I've asked students to actually, or I guess on projects, I've had students reproduce exactly what these results are without using the boot function itself. So make sure that you're able to do that. So what we have here for original, that's the original statistic itself based upon the original data. Here's that bias that we looked at, I think, last time, where you're simply taking the mean of all your t-stars, subtract off t, that's your estimate of bias. But now this is in a non-parametric setting. The standard error, no, that's just the estimate of the variance, the square root of the estimate of the variance of the t-stars. So in other words, this would be one way to calculate little v sub capital R. So again, to familiarize yourself with the notation that the book uses. So you could also say that this is, say, var star t star, an estimate of it based upon R resamples. Or you could also say this is var star subscript R t star. Oops, with a 1/2. Now, erase. Now let's use the plot function. Again, the plot function is generic in R, and so it actually calls a function called plot.boot. I think we've looked at this before. If you did class of boot.res, the class is boot. And here's a histogram of the distribution of t-stars. Notice how it is not symmetric, it's right skewed. Again, remember, you would think maybe the central limit theorem would work here, but then again, you only have a sample size of 12. We're interested in the sampling, that's why I brought the central limit theorem. And by default, also we have a QQ plot. This QQ plot is just drawn just a little bit differently from the QQ plots that I've drawn in the past. Specifically, quantiles of the standard normal are put down there versus, let's say, an estimated normal. So it just rescales the x-axis. And you can see there that it looks like we have some evidence against normality for the distribution of t star. Okay, page 45 then. Now, when I just simply say boot.res, it gives me a little bit of information what's actually inside of it. Does anyone know actually what functions is actually used when I just say boot.res? An actual function is used. Nope. This give me a tough question. Whenever you simply, say that, put the object in just say this, read this one. Whenever I just simply type boot.res, what actually happens is a function is executed. It's called print, in this case, .boot. So a little trivia there. Anyway, the results that are saved in boot.res are actually a list. And to help you, again, to learn more about R, and so that as we go along in this course, I need to bring this up less. You can look inside the function boot, and you remember here's the whole function boot. Okay, the very last line is what's returned to the user. And notice what it says here, boot.return, and it has a whole bunch of stuff in parentheses. What that basically means is it actually executes a function at the very last line called boot.return. So how would I view the function? Type boot.return, right? Uh-oh. What happened? Well, there are functions in R that are hidden. I really wish they weren't hidden. This started happening about probably about 7 years ago. I started hiding functions in R. I think just to clear up the clutter, because normally no one would ever actually execute boot.return on their own. And so, if you want to see any hidden functions, you can type a function called getAnywhere boot.return. Well, then the function's name. And this is what you get. So, notice what it says. It looked throughout to see if it could find a function called boot.return, and it found one in the package called boot. And this is what the function looks like. So you can compare, the function call there with what's actually used in the last line of boot.return. But the main reason why we want to look at this is that notice immediately you see something called out gets a list. Look what's down at the very last line, out. And the rest of the code that's in between just adds some stuff to out, like for example the class. It does some other stuff. Okay? You can look at it on your own, but the key thing is that notice that this is a list. So if what's inside of boot.res is actually a list, that means I can say names, boot.res, and I can see the names of the items in the list. So for example, one item, boot.res $T0, happens to be T. Another item, boot.res $T, happens to be all the T stars. So T star 1 is 113, T star 2 is 130.25. In fact, I can say boot.res $, let's say statistic. And there's the function that's used to calculate the statistic of interest. Note that boot.res $T is actually a matrix. Notice it has column 1, and it lists the remaining columns down there. I'm sorry, and then lists the rows down there. Suppose you want to see what the actual first resample is. This is useful in particular cases where you have maybe a more complicated statistic, and for some reason you get an odd result back for T star, or maybe the statistic for some reason couldn't be calculated. So you have to actually go back and look at your resamples. There's a function R called boot.array that allows you to view your resamples. So boot.array, first argument, boot.out, meaning what came out of the function boot. I save the results in boot.res. And there's one argument called indices. Indices equal true, which will help me see the actual indices for the resamples. I put the results into save.ind. And let's take a look at the head of it. So we see that we have 12 columns. And what this represents then is in the first resample, Y1 star was Y9. Y2 star was Y5. If I then want to see the actual Y values themselves, what I could do is simply say, let's take a look at the first row of save.end, and then combine that, or use those as my indices for Y. And so here's Y. So you can see the 9th element was picked first. That was equal to 100. Here's the 9th element. So what R is actually doing then with the boot function, it finds these indices, it passes them in as the I argument of calc.t. just to show you what would happen if I put false here for the indices argument. Let's do this. What do you think that is? Things being displayed. I still have 12 columns. Frequencies, exactly. So twice I got Y1 in my first resample. Here's one time. Here's the other time. Remember how you can think of also the bootstrap in terms of the non-parametric bootstrap. You can think of basically a sampling with respect to a multinomial distribution, where all the observation numbers are categories. And here are the frequencies from taking a sample from the multinomial. And again, that aspect is helpful in various proofs at times when you need to prove something with respect to the bootstrap. Page 46, as I have listed there, an instructive activity is to actually put something like this into your calc.t function. So now I put print I. What this is going to allow me to see is that when I run this, it's going to allow me to see the indices that are passed in. So I'm going to highlight that so I get a new calc.t, and then I'm going to run the boot function again, but this time just one resample. And let's see what happens. Okay, so the first time that calc.t was called twice, as we see here, not just once. The first time through, it calculated the original statistic, or I'm sorry, calculated the statistic on the original data. So this is where T0 comes about. And then here's my first resample in terms of indices. So again, putting little print statements like that, or I could use the cat function as well, is helpful to, again, diagnose things that might be going wrong. We maybe have more complicated data structures as we go later on. That can be helpful. Okay. Once you take out your book and go to figure 2.7, on page 26. As I mentioned before, and I will mention again, it's helpful to bring your book to class every day, for this class especially. What I like to be able to do is reproduce that top plot there. And this is somewhat similar to a plot that we saw before with the parametric bootstrap with this data. And that is, I want to look at, well, how large of an R do I need to use in order to get a good estimate of my quantiles for my G hat distribution. Remember, T stars distributed G hat. And so what we can see in that plot that, that these estimates for the quantiles, this is 4 simulation runs basically, per quantile, where we're looking at the 0.05 and 0.95 quantile, we see that maybe about after 500 resamples, the quantiles don't change too much. So with that as background then, let's talk about the code that can be used then to reproduce this figure 2.7. A lot of the code is very similar to what we did with a parametric bootstrap, so I'm not going to go through it line by line, but I'm going to point out the important parts. First of all, for all the R values I'm interested in corresponding to that plot, I just create a vector that contains them. Save 2 is a data frame that's going to allow me to put my results in. P05 corresponds to percentile, fifth percentile, or you say 0.05 quantile. P95 corresponds to where I'm going to put the 95th percentile. And then I do my simulation basically with 4 runs. I do the boot function every time, use a counter, and then I find the quantiles corresponding to, look at what, boot.res $T, T star, well, this is going to be given, is going to be T star 1 all the way up to T star I, where I corresponds to either the 19th, 39th, the 99th, 199 value. That's in R values. I'm going to find the 0.05 quantile, do that for the 0.95 quantile, save all the results. And produce a plot in a very similar manner to what we did last time. Okay, this is what I get. So we have 4 simulation runs again. And as you can see that as R gets bigger, that these quantiles of T star minus T, that distribution, end up getting to about the same spot, and they don't change a whole lot. I think from looking at this plot, I'd be more satisfied with taking R equal 1,000 versus in the plot given in the book. I think they were satisfied with R equal 500. So this is again just to show you that you need to take a large enough number of resamples in order to estimate quantiles. But also what this plot shows you too is the black lines there correspond to quantiles that are the true quantiles from the parametric bootstrap setting. So when y was distributed exponential, we showed that T star was a gamma n comma y bar. So I found the 0.05 and 0.95 quantiles. So are you concerned at all that the non-parametric bootstrap is not agreeing with what the parametric bootstrap would tell us? Excuse me?
It's not bad.
It's not bad. Not as good as we like it, definitely.
But again, we have a small sample size.
But the key thing to think about here is that, remember with the parametric bootstrap, we had to initially assume y is distributed exponentially. Maybe that assumption was wrong. What this non-parametric bootstrap is saying is that, oh, I think you have more variability than what you're accounting for in the parametric bootstrap. Okay, so page 249. Now you can also see then the differences between what the non-parametric bootstrap and the parametric bootstrap give you by looking at figure 2.8 in the book. On the left side, sorry, it's page 220. It's page 26. What you see on the left-hand side is a QQ plot, where you have values of T star on the y-axis. And on the x-axis, you have what the quantiles would have been if we would have started off with saying y is distributed exponential. And you can see differences there between the quantiles. So that's why maybe what we're seeing here through using a non-parametric bootstrap is that our parametric assumptions maybe are not good. But again, we only had a sample size of 12 to begin with, and it was kind of hard to make a really good judgment of, well, is exponential good or not? We looked at a few different plots and thought, it might be reasonable, but maybe what we're seeing here is not evidence that it wasn't. Okay. But also the authors for this particular example decided to look at, well, what would have happened if we started with from the perspective of let's see, y was actually distributed gamma instead. So I have an additional parameter to work with. So whenever you have an additional parameter, do you think your model is going to fit better or worse? It's going to fit better. Okay? Maybe not significantly better, depending upon the instance. but you would expect it to fit no worse. Let's see if maybe a gamma would have been better to use in this particular situation for a parametric bootstrap. So to do that then, we need to think, well, what would be y star? So if y is distributed gamma kappa mu using our book's notation, y star, of course, would be gamma kappa hat mu hat. So in other words, this is, let's say, f hat with respect to a parametric bootstrap. Well, what's kappa hat mu hat? Well, use maximum likelihood estimation. Seems like a reasonable thing to do. So let's take a look at the likelihood function. So this is what the likelihood function looks like, again, using the notation of our book. You know, you can do some nice little simplifications here. You know, you can factor out the gamma of k, you can factor out actually a bunch of stuff. And in that product there, you're only left with the product of y raised to the k kappa minus 1 power. Then what do we do next when we do maximum likelihood estimation? Well, we find the log likelihood function. So there's the log. And what do we do next? Take derivative with respect to kappa. Take the derivative with respect to mu. Set both of them equal to 0. Solve. Guess what? It's not a closed form solution. So what do? Numerical estimation. Exactly. By chance, do you ever do that in 883?
Numerical estimation.
Yeah. Like how do you do numerical estimation? I'm just curious. Excuse me?
I don't know.
Okay. Is there a particular function that you look at, or do you just... Anybody else remember from 883? Well, that's good that you do. I'm glad that you do talk about numerical estimation. Because, I mean, obviously, especially once you get into the other classes, I mean, that's what you have to do all the time. But typically what I find for students typically what I find for students in this class and in other classes, you know, you're not necessarily comfortable with just starting from scratch in terms of if I give you this likelihood function, I want you to find what the parameter estimates are using numerical estimation. So what I want to do is take some time to talk about how to do that because it will come in handy later. And also, this function that we're going to talk about, it's a very, very useful function. I've used it many, many times in my research because it allows you to do this numerical estimation here without ever having to actually calculate derivatives yourself. You know, depending upon what function you're trying to maximize, it can be quite useful. Okay. So, whenever you do a numerical estimation routine, you're going to need to find places to start off your parameter estimates at. And, well, how about we simply use the MOMs, the method of moment estimators. That seems nice because you can come up with nice little closed form solutions. So again, an 883 review. Find the expected value of y. In this case, it's mu. The variance of y is mu squared divided by kappa. I've already presented that before. But what do you do when you find method of moments estimators? Next.
Oh, wait a
Set the parameters equal to their moments. Their observed moments, you could say. And depending upon what you want to do, I'm going to set this equal to the unbiased estimate of the variance. And now if you solve, you got two equations, two unknowns, and they can be solved. And you can show that mu, let's say tilde, is equal to y bar. Kappa tilde is equal to y bar squared divided by s squared. So what this gives us are a place to start in our numerical estimation routine. Next, what we need to do is actually program the log likelihood function. So Here's the structure that you would want to use in R. Create a function. In your first argument, have your parameters that you can pass into the likelihood function. So I call it par.gamma. Parameter is gamma. This is going to be a vector, where the first element, I've decided to let that be correspond to kappa. Second element, mu. Next, I pass in my data. So I calculate my sample size, and then I actually put into the correct R syntax the log likelihood function. So in that log likelihood function, you'll notice that there is for example, a log of a gamma of kappa. Well, in case you have come across this before, there's actually, in statistics, we come across this a lot, typically a function in a software package called L gamma. I think SAS has that as well. So it comes up in various places. So they actually have a function called L gamma that calculates this log of the gamma function. And you can look at the details on your own. It's important that you do fully understand how I programmed in this likelihood function, or log likelihood function, into R using the correct syntax. And also how I take advantage of vector calculations. So for example, at some point I'm going to need to find the log of y1 plus log of y2 plus log of y3 down to log of y12. The most efficient way to do that is use log data. So what log is going to do is actually calculate using the log of every single element in that vector, and then to use the sum function to sum everything up. Last, right here, I have a negative sign. So actually what this function is going to do is find not the log likelihood function, but the negative log likelihood function. Here's the reason. The function that I'm going to use to actually find the maximum likelihood estimates, the function is called optimum. Optimum minimizes a function of interest. I want to maximize. I want to find the maximum, though. So what do? Well, I minimize the negative log likelihood function, which will be equivalent to maximizing just the log likelihood function itself. So that's why I've coded it this way. In some recent versions of R, since so often we want to find maximum likelihood estimates using this optimum function, in some recent versions of R, they've actually added an argument that allows you just to program in the log likelihood function itself, and then through using an argument, control equal list fn scale equal -1, you can now maximize the function. You can use it if you want. It's just when I was updating my notes, actually I came across this in my research in the last year. There is now a way to get around this kind of odd aspect of having to minimize the negative log likelihood function. In the end, you get the same answer, so no big deal. Okay. Let's see. So I need to find starting points for my parameter estimates, and this is where I use then my moms. So I just program in the function for the moms, and then I use optimum. Again, as I said, this is a great function. I love this function. I wish I knew of this function when I was doing my dissertation. When I first found out about this function a number of years ago, I was like, oh my gosh, this makes life so much easier. So the first argument is called par, standing for parameters. And so I have a vector of parameters. It has to be in a vector. Then fn, my function that I want to minimize. I call that function log L. Then optimum, if you look at the help, there's a ... argument, meaning that you can pass in additional bits of information into Optum, and it will carry it through and use it when needed. So for example, I have an argument called data. Data equal y. Guess what? That isn't touched by Optum at all until it calls the log likelihood function. So that's how I get my data into my function. Then I use the control argument. That allows me to control various aspects. And I say you can take a look at the help for Optum to see the various arguments that you have. I have trace equals 0 here, so it doesn't tell me, doesn't show me every single iteration. If you do something else than trace equal 0, you'll see bits and pieces of iterations. Maximum number of iterations, 10,000. I just put that there just to let you know that this kind of stuff exists. You can control this stuff more. Method. The default method in Optum is what's called a Nelder-Mead way of optimization. I had problems with convergence. So I look at the help for Optum. I noticed there was a whole bunch of other ways that it does this numerical estimation. I found one called BFGS. Look at the help if you're interested in knowing more about that. In our class, that's not an important aspect. If we had, let's say, a numerical optimization class, that would be important to know. What does it do? Hessian equal true. What do you think that does? What's a Hessian matrix? You ever heard of a Hessian matrix before? Well, it's going to be very helpful to use to do something with Fisher's information. Hessian matrix. It's a matrix of second partial derivatives. Matrix of second partial derivatives. And why is that important? Because the observed Fisher's information matrix is the inverse of the matrix of partial derivatives involving a log likelihood function. It's a negative. It's the negative of the that matrix. And why is Fisher's information matrix? I'm sorry. I don't think I said that right. Okay, Fisher's information matrix is the negative of the Hessian matrix, where we're evaluating the log likelihood function. Okay. Now, why is knowing the Fisher's information matrix important? Variance estimation. So, what would be then the covariance matrix here? The inverse of the Fisher's information matrix. Very fundamental aspect to statistics. If you have not heard of that before, you need to learn more about that. I would assume Stat 971 would cover that kind of stuff. Okay? If you haven't had Stat 971, you should take it. But it's a very fundamental concept. I can give you some references on this. One reason why I bring this up, to tell you a little story. I just finished my master's degree, and I was in my first semester of the PhD program, and I was taking a survival analysis class, and I was having a hard time. The first homework assignment that my professor gave was very, very difficult, at least for me. I was starting to doubt myself. Can I do the PhD program or not? And one of the things that the instructor asked us to find was to find the Hessian matrix. I had never heard of a Hessian matrix before my first 2 years of grad school. He explained it to me and said, well, now you know what it is. Go calculate. And I was able to do it. And things turned out well for me in the PhD program, and now, without filling in all the blanks there. But, so, let's actually run this Optum function. I'm going to put the results into save.optum. It gives you a list back. So if I just type save.optum, In this particular case, there's not actually a print function associated with it, so you actually just simply see what's inside the list. Here's kappa hat, here's mu hat, the maximum likelihood estimates.
The method moment estimates?
Maximum likelihood estimates. I use the method of moment estimates as its default as its initial values.
Okay.
Sorry if that wasn't clear. So this is the maximum likelihood estimates. This value, this is the minimum of negative log likelihood. So the maximum of the log likelihood function, where it obtains its maximum, is negative 67.64. Here's some information about the numerical estimation, or the, in terms of like the numerical estimation. It's not going to be very important for us, at least in this class. Convergence, a 0 means convergence, something else means you got a problem. So look at the help for the other values that convergence can take on. And here's the Hessian matrix. Okay. So if I want to find now then the covariance matrix, and this is the most important thing to get out of it, at least in this class, I need to take the inverse of this. How do I take an inverse of the matrix of R? Does anyone know? You can't do it, you have to do it by hand. Anyone know how to take an inverse of the matrix? There's not an INV function, which is quite confusing to introductory students to R. Solve. Thank you. So I can use solve. And there you go. So basically using I took the inverse of the observed Fisher information matrix, and 0.06 is the estimated variance of kappa hat. So it's like var hat kappa hat. Var hat of kappa hat. 1377 is var hat mu hat. Var hat of mu hat. And this actually all this relies on is the large sample distribution for maximum likelihood estimates. In fact, in my 875 class, that's something we talked about in Chapter 1. This is just a direct application of that down to gamma distribution. So now that I have that, then the whole purpose of doing this is so that if I were to do a parametric bootstrap, I need to know what G hat is going to be. Now that I know what these parameter estimates are, I can find G hat. But one little thing here, as I mentioned before, I have little problems with convergence. And so whenever you have problems with convergence, and especially when you just have a small number of parameters, what you can do is you can take a look at the likelihood function itself, or log likelihood function itself. So here's a contour plot of the log likelihood function. Load this up a little bit. And the blue lines there are corresponding to what kappa hat and mu hat are. And we can see the surface, represented now in 2 dimensions in terms of the contour plot, is coming up to a point right here. And one thing that you'll notice is that here's the negative 68 contour. Remember, the maximum of the log likelihood function was negative 67.64. So what's happening here is that this is kind of flat. And that's probably why I was having problems with respect to convergence. I guess that's more of just an interesting side note. Okay. So T star then, well, we know what Y star is. Y star is distributed gamma, kappa hat, mu hat. Using properties of gammas, then I know that T star is gamma and kappa hat, mu hat. And so what we can do is, since we have this distribution, we can now do some QQ plots and compare quantiles from the non-parametric bootstrap for T star and now a parametric bootstrap for T star. And that's what's represented in the right-hand side plot of figure 2.8. Or alternatively, what we can do is look on page 253 where I have reproduced the plot. So what do you think about starting off with y distributed gamma? Looks pretty good. So that extra parameter is really helping us. It's getting the non-parametric bootstrap to agree with the parametric bootstrap. If I would see something like this, I would be satisfied with using a parametric bootstrap. Again, we have a little deviation on the right-hand tail, but remember, we have a right skewed distribution, and so it's going to be very hard to get at those quantities out there. Okay. Lastly, then, in this particular section, we need to talk about discreteness that occurs when you are using a non-parametric bootstrap. There are a finite number of possible resamples, as you know, and this can lead to discreteness that you see in plots. And I think the plot I want to reference figure 2.9, page 28. I actually, since it is a good plot, I've actually reproduced it here, and I have some writing on it. You can ignore the writing for now. What you will see in a non-parametric bootstrap setting is some discreteness, some banding in the plots. First of all, though, let's talk about this left-hand side plot here. This is using the parametric bootstrap. The authors found basically y bar star, assuming that y was distributed exponential, so they went back to that assumption. Y bar star here, and then also then the standard deviation for each resample. Okay, and just look at the relationships between the two, and you can see that there's no necessarily any kind of banding here, as you see in the right-hand side plot. Where in the right-hand side plot, I'm using a non-parametric bootstrap. So essentially, what we just were doing with non-parametric bootstrap. Okay. Now, why? Now, when you see a plot like this, and they just shows to plot these particular values, you can plot other ones too, and you might. But whenever you do a plot like this, you might be starting to get worried about, did I do something wrong here? Why do I have this banding that occurs there? Well, the reason why this occurs is, again, because of the discreteness that occurs when you're doing a non-parametric bootstrap. There's a finite number of possible resamples, and thus there is a, there are going to be times where, you might get, this is represented here, you might get the largest value in your data, which happens to be 487 if you look at the vector y. You might get that 4 times. Or you might get it 3 times. Or you might get it 2 times. And so what I've done here is I've actually circled there for you, showing you how many times, just look at the red, don't look at the blue, how many times that you get the largest value in a particular resample. Now, within each of the red ovals that I've drawn there, you can see another banding pattern. And that corresponds to now the second largest observation. So if we look at then this bottom one here, we see that the second largest observation is 230, and that appeared 4 times in the top band, 3 times in the next band, and so on. This is not necessarily something to be worried about when you see this banding. Now you can see, though, that if you have a large outlier in your data set, that this banding is going to be more pronounced. And in fact, you might end up having some problems. So you might be thinking, well, geez, are there particular diagnostics that you could implement, similar to like regression diagnostics, to help you determine, do you have problems with respect to using the bootstrap? Yes, we do have them, and that's going to be the subject of Chapter 3. But it's good to point this kind of stuff out now so that you don't get worried when you see some plots when you don't need to be worried. Okay, any questions? Okay, let's take a look at the project.
I have a quick
Yeah.
question. On your graphs for your QQ plots
Mhm.
that we just looked at, on the bottom of both of them it says gamma quantiles.
Yeah.
Should the one be X?
Yeah, I understand that I use a different x-axis label for the for this one here. I thought their x-axis label is a little misleading because what we're doing here is still finding T star, and if you start with a exponential distribution, it's distributed gamma.
Okay.
Okay, so that's why, because we were actually putting gamma quantiles there versus the book they say exponential model quantile.
Okay.
Okay. So let's briefly go through the problems that we have not done yet. So problem number 1, it's again taken from basically the cell inverter, or modified from the cell inverter, motivated by the cell inverter. And there's our very, very small data set. And we already talked about part A here, find how many possible resamples are out there where they're not necessarily unique resamples, so the order of the numerical values does not matter. So we already talked about that. And I want you simply to actually list out all the possible resamples. Don't worry, you'll be able to list them all out. There's a large number yet, but it's not that large. There's a variety of ways that you can do this in R. So I wouldn't be surprised if some students find different ways to do this. Then part C, find T star for each resample. Let's construct a histogram for that. And what that will give you then is the actual true, or at least a visualization of G hat. Where notice I didn't put a subscript R there, because you were looking at every single resample. So that's the distribution of T star. Part D, we talked about how many unique resamples are possible. Part E says give the actual probability distribution for T star. So what you end up having to do there is actually looking back at part B. You have all possible resamples, and then I guess also part C, and you know what all possible T stars are. So what you basically need to do is find a relative frequency distribution. And that is the true distribution again. It gives you all the it will allow you to find all the probabilities. And again, we just make sure we can do this because we have a very low n. If you have anything that's larger than 4, you're going to have problems. As we'll see, number 3. So now, actually find what the expected value star T star would be. Now, the expected value star given F hat. Find the variance find var star of T star as well. Show your calculations using this probability distribution that you found in E. So, in other words, what you will learn in Stat 882, using that particular formula, show me how you would calculate that. Now, I should mention, sorry, I forgot to mention this, the sample mean is T. Now, in the notes last time, we actually derived closed form solutions for what this expected value in this variance would be. So you should have them match. And then last, yes?
Sorry, for the E star, T star that you have kind of outlined in the rectangle there, can we do that in R, or do you want to show us by hand?
Well, do it in R.
Okay.
Because there's going to be too many values to write out, let's say.
Yeah, okay.
And then part G, can cell inverter actually give a slightly different value for what they call the bootstrap variance? In other words, this right here. Well, tell me why that happens. And I'll give you a hint. It's something in the text in chapter 10. Look at how they. Yeah. Take it. there's something in the text, you'll see the formula and say, oh, yeah, that's fine. Okay, so that's number 1. Then number 3. This is based upon number 10.14 in Kinsella and Berger, Part A. We're going to be working with the sample variance, just like what you did in number 2. So now T is the sample variance, the usual sample, unbiased sample variance. Now, in number 1, we were able to you can actually find var star T star. You can find the actual value without actually physically taking resamples. Well, you can also find var star T star as well when T is the sample variance. I want you to do that here for this particular example. And it relies on, to make this easier, number 5.8b of Cassell and Berger. They give, and you can just use the result, you don't have to prove it, they give what var s squared would be. Using the results and some relatively minor modifications, you can get what we would call var star T star. Give me the actual formula for it, and then give me the numerical result using the data that corresponds to 1014 Part A. Now, also in number 1, we looked at how you could, if you had the actual probability distribution, how you could actually find var star T star using STAT 882 methods. Well, that involves getting all possible resamples. Guess what? You can't do that here with 32-bit R. Tell me why. Try it, and you'll see something that pops up. Don't need to say why.
Question on that. With B and C with the extra credit, what if the version you have installed is 64-bit
Well,
already?
32 and 64-bit are both
Okay.
automatically installed.
Okay.
So they are automatically installed anytime that you install R.
Okay.
So just go under.
So when you're
Start here.
opening R, make sure you open the 32-bit.
Yeah.
Okay.
Yep.
Okay.
And you'll know if you open it up by, we'll say when in our console,
Yep.
32-bit. Okay. Now, a few years ago, 64-bit R came out. And why do you think 64-bit R was something that people would like versus 32-bit? Does anyone know why?
Do this?
Well, I was unable to do it. That's one reason why it's extra credit. But I would think it could be done, and so that's why I made it, still giving it an extra credit. But why do you think 64-bit R was an improvement over 32-bit R? Anyone know why 64-bit computers are nice compared to 32-bit computers?
Because they can handle larger numbers of things.
Larger what?
Like larger numbers and larger amounts of things.
We'll say larger amounts of things. It's one way to say
Highly technical speak.
32-bit computers has a maximum memory of 4 gigabytes of RAM, okay? In terms of the number of possible addresses that you could have in your computer's memory. It's actually, for most computers, it would actually be a little bit less than 4 gigabytes because certain parts of memory are reserved for certain things, but we'll just say 4 gigabytes is the max. When you start now using 64-bit, now you have access to a whole bunch more memory. And there are many things out there now that can be done with all this extra memory. So for example, I have a computer in my office that has, I think, 12 gigabytes. This computer has 8. Now, with respect to R, the reason why that's so important, I'm probably giving away the answer here, but for B, but oh well. The reason why that's so important is because anytime you create an object in R, where is that stored? In memory. If you create a data set in SAS, where is it stored? Is it stored in memory? No, it's stored on disk. So one problem that people have had with R, and also, let's say, versions of S Plus that maybe were even done on a 16-bit computer in the mid-1990s, is you were limited by the memory that was on your computer with respect to how big of a, let's say, data set you could have. So you can think of the number of, if you list out all resamples, that's a data set to some respect. It's not called a data set R, but I think you get the idea. So hopefully, you can keep track of all that if you have the RAM. Okay, I've said enough about that. We'll move on. Part D. Use the non-parametric bootstrap with actually taking resamples to estimate var of t. So in other words, you are calculating little v subscript capital R. That's my estimate. You should, again, I don't know, I should keep on doing this, but you should think of the other notation equivalences for how that's represented. Set a seed right before you use the boot function because I want everyone to get the same results. It makes my grading a lot easier. And compare your results to those obtained in Part A and in number 2 when you were using a parametric bootstrap. Remember, in number 2, we were actually using the true distribution from which the data supposedly was sampled from, according to Cassell and Berger. Part E, well, this is directly with something that we talked about today. Tell me what the first resample is. Just kind of prove to me that you can use a particular function. Part F, construct a histogram and EDF of the t-star values obtained in D. Include on the plot the distribution for t-star from 2. So I want you to see, well, does the non-parametric bootstrap agree with the parametric bootstrap? And part G involves doing some confidence intervals, which we are going to do next. Are there any questions? So that's pretty much it for project number 2. The last thing that we need to cover is the confidence intervals for both number 2 and number 3. Okay, so let's take a look here. Since we're running out of time, I will just go down to here and stop. So I want to find a confidence interval. This is the first time now that finally we can really perform inference using the bootstrap. And once we have this as background, that will allow us to do some interesting examples. And we're going to talk about 2 different kinds of confidence intervals using the bootstrap in this section. Chapter 5 is a whole chapter on bootstrap-based confidence intervals. The authors decided just to do 2 here, 2 simple ones, so that in chapters 3 and 4, before we get to chapter 5, you can do some stuff, some inference. And first of all, we are going to be interested in a confidence interval for theta. We're going to define a lower bound, let's call it L, and an upper bound called U. But look at what we call this, or look at the confidence level, how it's stated. This is the book's notation. 1 minus 2 times alpha times 100% confidence level. And normally we state this as a 1 minus alpha times 100% confidence level. So essentially, all that's occurring is this. It's just a different notation. This is the only place I've ever seen it, though. So let's say if I want to find a 95% confidence interval, normally we would say, okay, alpha is 0.05, and if I find a confidence interval for, let's say, mu, with using a t distribution-based formula, I would find, let's say, the 1 minus alpha divided by 2 quantile from a t distribution, and minus 1 degrees of freedom. Now, so in this case, I would use alpha 0.05, and this would be 0.975, right? Now all we're saying is this, that our alpha in this particular case is going to be 0.025. So now if I were to use then the notation on our book, we would find the t, the 1 minus alpha quantile from a t distribution with n minus 1 degrees of freedom, where now alpha is 0.025. You get the same thing, it's just different notation. That's it. So in order to find then this confidence interval for theta, everything comes from knowing the sampling distribution for t minus theta. And that sampling distribution we denote by g. And that's why we spent so much time so far in this class figuring out how can I estimate this sampling distribution. Once I have that estimate, now I can find confidence intervals. We will stop there. Are there any questions? Okay. So that is all for today.